The same computation can be done in different ways on an FPGA, and we will talk about pipelining and parallel processing and see that there's a trade-off between the number of logic elements used, the throughput, and the latency. Let's assume an external sensor is generating data. It will give us a floating point number x. We need to compute this Chebyshev polynomial of x, and then the output is going to go into some other finite state machine on our FPGA board. So we have a sequence of numbers coming in from our sensor. We have to apply this computation, and then we have to give it to some other finite state machine. And since our finite state machine is operating once every rising edge of the clock, we need to be able to do this computation in a time shorter than the clock period, because at the next rising edge we have to have the next number ready to go into our finite state machine. Tangentially, it is remarked that although in principle this is combinational logic and can be implemented using a lookup table, that is almost never a good idea. The lookup table would have to be super enormous. If we have a 32-bit floating point representation for x, then we need 2 to the 32 entries in our truth table or lookup table, etc. Conceivably, we could use memory. We need probably a bit over half a gigabyte of memory to store a lookup table for this. But again, that's not a very cost-effective way of doing things. So just like humans do arithmetic by following rules, remember to do long multiplication, you multiply first by one digit, then add a 0, multiply the next digit, then add up the answer, etc. Basically, that's how floating point arithmetic is done in practice. It's more efficient that way. And we can download code from Verilog code that other people have written that implement floating point operations. And for this example, we're going to assume that we have modules that can do our floating point multiplications and additions, etc. We're not so much worried about those details. We just want to have a look at roughly what are the basic steps we need to do to compute this, and are there different ways of arranging the steps in order to get computations which might be more favourable for certain applications. Here is one possible implementation of our Chebyshev polynomial. We assume we have got floating point blocks that can compute the product of two floating point numbers over here and over here, and we have floating point adders over here. For convenience, I haven't drawn all the wires, but the yellow labels, you just pair them up. So x to the power of 10 goes to x to the power of 10 here, x to the 8 to x to the 8th, x to the 6th to x to the 6th, x to the 4th to x to the 4th, and x squared to x squared. Over here on the left, with x going in, x times x gives us x squared times x squared gives us x to the 4th, and x to the 4th times x to the 4th gives us x to the power of 8. To get x to the power of 6, we multiply x squared with x to the power of 4, and to get x to the power of 10, we multiply x to the power of 8 with x to the power of 2. So this part produces all the powers of x that we need, and over here we multiply each x with its coefficient and add it up here. This is not an optimized implementation at all. It's just explaining one way this can be implemented. The key point is we call this an all-at-once implementation. We don't have any flip-flops anywhere to break up this computation. The input comes in and it's going to have to trickle through all these units, and when the answer's finally correct, that's how long it takes to do this computation. It's done all at once. The time it takes limits how fast we can process the data. Remember, the sensor's generating data and it's coming in here at the x, and then the output here is going to go into some finite state machine. And the finite state machine will be reading the number here once every rising edge of the clock. So if the sensor's generating data quickly, then we have to process it within one period of the clock in order for it to be ready to go into our finite state machine at this end here. Before looking at alternatives, let's look at the basic idea of pipelining. Let's consider making chairs. One option is that one person can make a chair himself. Another option is that the making of the chair can be broken up into 3 parts. Perhaps the first part is cutting the wood, the second part is assembling the wood, and the third part is painting it. Either way, the output is going to be 1 chair. There is a difference though in the throughput. If it takes one person 1 day to make a chair, then in this approach we can only produce 1 chair per day. In this approach though, we can produce probably 3 chairs a day. The task of each person is approximately 1/3 the task of building the whole chair. So in 1 day, this person can prepare the wood for 3 chairs, this person can assemble the wood for 3 chairs, and this person can paint 3 chairs. So this pipelining approach, this assembly line approach, is going to produce 3 times as many chairs as this approach. So pipelining increases the throughput. There is a potential disadvantage, and that's the latency. So in this approach, if we time how long it takes from start to finish to build a chair, usually this approach is going to be the fastest. This approach here, unless the division of time exactly splits into thirds, we're probably going to find that, say, assembling the chair might take a bit longer than cutting the wood, which might take a bit longer than painting. But because this is a pipeline, then we're slowed down by the slowest person here. So the length of time it takes from when we start to produce a chair to when that first chair rolls off the assembly line, that's known as the latency, that's going to be, in typical cases like this one, it's going to be 3 times the time it takes the slowest person to finish their job. And usually that's going to be longer than this one here, unless all times are exactly equal. So it's pipelining, or using an assembly line, is a trade-off between throughput, how many chairs we can make, versus latency, the time from when the materials go in to when you get your next chair. In making chairs, the latency might not matter very much if it's in continuous operation. It's if you're starting and stopping. If you suddenly get an order for an exotic chair, then maybe the latency matters. That's how long the customer's going to have to wait for that particular chair. But if this is running normally, then the latency doesn't matter normally, because all that matters is how many chairs you're producing, if you're producing them continuously, and can you sell them. If we go back now to our digital system problem of sensor data coming in and then being processed here, whether the latency matters or not depends on the application. If we have to detect a fault event very quickly, then latency might matter. On the other hand, if we just have to process all this data, an extra increase in the latency by a little bit isn't really going to affect anything. And in that case, being able to have a much faster throughput, a much higher throughput, is usually much more important. It means that in processing our numbers, we're storing intermediate results and doing smaller computations, and so the result will ripple its way through here and coming out with the final answer. And since we can be doing many things at once here, we end up with a much higher throughput. Let's try to make this concrete for our example. Here is our all-at-once implementation, and we'll convert this to a pipelined implementation. Recall that a pipeline means that we've got a worker 1 here going into a flip-flop, going to worker 2, going to a flip-flop, going to a worker 3, a flip-flop, and so forth. And I'm not going to draw it because it'll get messy, but I'm going to describe what each of these workers do. And just remember, the first worker does his or her job. That then gets at the next rising edge of the clock. That then gets passed on to the next worker, who can then process the input numbers and produce output numbers. And this goes on down this pipeline until finally at the end we have the answer that we want coming out here. Just like in making a chair, we can break it up into 3 parts. This computation here can be broken up into many smaller parts. By pipelining it, we significantly increase the throughput. Yes, we have a longer latency. It might take longer for our very first number to appear at the end, but we can process many more numbers per second with a long pipeline like this than with the all-at-once approach here. Our first worker is going to compute x squared, so x comes in. Our first worker is going to compute x squared. Our second worker is going to compute x to the power of 4, so our worker 2 will compute x to the 4. And to be efficient, our second worker is also going to compute 50x squared. This just means the output has got more wires than the input, but that's okay. The third worker can compute x to the 6th because both inputs are available. It can also compute x to the power of 8 for the same reason, the inputs are available, and it can also compute minus 400 x to the 4th for the same reason. Then we move to the fourth worker, and the same thing, we just look to see what inputs do we already have. So the fourth worker can compute this, the fourth worker can compute this, and the fourth worker can compute this one here. That leaves the fifth worker to compute this one, and then it depends how many more pipelines we want. If addition is a slow operation, then we could have worker 6, worker 7, worker 8, worker 9 to do these additions here. If addition can be done a lot faster than these multiplications here, then we can combine some of these additions. Although we still have to do one addition after the other, if we can do 5 additions faster than we can do a floating point multiplication, then our last worker can do all these additions for us. By breaking it up this way, the worker who's got the most work are the workers that have to compute these floating point multiplications. So however long that takes is going to determine the smallest possible clock period that we can use. That time is going to be significantly shorter than our all-at-once implementation, which requires up to 9 or 10 times the amount of time we get by breaking this up into the smaller parts here. Revisiting throughput and latency, consider these 2 different implementations. In this implementation, we do 2 operations at once. In this implementation, we've pipelined it by breaking up these 2 operations and putting an additional flip-flop in the middle here. Let's add some timing information to this example. Let's assume that combinational logic 1 takes 10 microseconds to complete and combinational logic 2 takes 15 microseconds to complete. So 10 microseconds here, 15 microseconds here. In total then, it's going to take 25 microseconds to compute this. This limits the clock period to no less than 25 microseconds in this top example. In practice, there's going to be minor delays in the flip-flops themselves, etc. So we're not going to be able to achieve this. We're going to be able to produce, at most, one number every 25 microseconds. And that'll be a bit less due to the additional delays in the flip-flops. So the throughput in the first example, if it were ideal, then we'd be able to get one operation per 25 microseconds or 40,000 operations per second, meaning every second we can be producing 40,000 numbers coming out here through this pipeline segment coming out. 40,000 numbers being processed per second. The latency is how long it takes for a number to go from start to finish. And in the top example, if we ignore any delays in the flip-flops, then the latency is going to be 25 microseconds. If we now look at the second example, then the clock's period, it has to be sufficiently long to accommodate the slowest worker. In this case, the slowest worker is CL2, taking 15 microseconds. So the clock period must be longer than 15 microseconds. The flip-flops are going to have some delay, so we're going to have a longer clock period, but if we assume everything's ideal and we operate this at the fastest possible frequency, then our clock frequency is such that its period is 15 microseconds, and that will determine the throughput. So in both these examples, the throughput is determined by the clock rate. We have one number coming out per rising edge of the clock. So very often, not always, but very often the throughput is equivalent to the clock frequency. It's just that the clock frequency is in hertz and the throughput is in operations per second, so the units are different. In these simple configurations though, clock frequency and throughput are going to be the same numerical value because we're getting one number coming out per each rising edge of the clock. Anyway, in ideal circumstances, this second implementation here can be producing 66,667 rounded off operations per second because it's determined by the slowest worker here. We notice that by pipelining, we have significantly increased our throughput. Had these two tasks been of equal time, then we could have doubled our throughput. Very rarely is that the case, but we still see a noticeable increase in the throughput. We do, however, have a longer latency. Indeed, in these idealized examples, the latency is also determined by the clock period because it's the time it takes to go through here, and we're assuming the flip-flops are ideal with no significant delay. And so in this case, even though this worker finishes in 10 microseconds, it still has to wait for this worker to finish before everything is clocked on to the next person. So in this case here, we see that the latency, if we're running at the fastest possible clock frequency, then the latency is going to be 15 microseconds to get through here and another 15 microseconds to get through here, giving us a latency of 30 microseconds for our pipelined implementation. So we see we have a trade-off. We are prepared to have an increase in latency, which is a bad thing, in return for an increase in throughput, which is a good thing. There is an alternative to pipelining, and in fact it can be used in conjunction with pipelining, and that is parallel processing. The idea is very straightforward. We won't worry about the actual implementation. We'll just discuss the basic idea, which should be clear. As always, we have a stream of numbers coming in. Maybe we have 1 million numbers per second coming in, for example. And assume that we can process them. We want to process them through some combinational logic, but the delay is such that we can't keep up with processing 1 million numbers a second. Well, we can just hire more people to do the work. So I can duplicate my combinational logic as many times as I like, except of course we might run out of space on the FPGA. So that's the trade-off here. The trade-off here is the number of logic elements used, because if we use too many logic elements, we have to upgrade our FPGA to a more expensive one, and eventually we'll get to such a large number that there doesn't even exist an FPGA with that many logic elements on it. But there's a trade-off. If we can afford increased real estate, then the idea is very simple. We just have some sort of a mechanism to distribute the numbers evenly across these 4 processors, and some other mechanism here to gather the data and put it back into a serial stream. So if, for example, the numbers 1, 2, 3, 4, then 4 come in here, we'd send 1 to this one, 2 to this one, 3 to this one, and 4 to this one. And then this produces the outcome first because it got the first number, and then we just convert this back to a serial stream of numbers here. So we process this one, then this one, then this one, then this one. So by breaking it up, distributing it across workers and recombining again, then we get an increase in throughput by however many workers we have. In this case, our throughput has increased by a factor of 4. Our latency, apart from any extra time required to distribute the load and gather it back up again, our latency is pretty much unchanged. The main penalty is we need 4 times as much area, 4 times as many logic elements, plus some additional logic elements to implement the distribution and gathering operations over here too. So if we can afford the extra logic elements, then this is a very nice way of getting a greater throughput without very much increase in latency at all.